You know, that simple act of plugging something into the wall, it feels so straightforward, but there's a whole lot more going on than you might think. The AC power that comes out of our outlets isn't just one simple thing. It's actually a hidden, complex world, a secret dance of energy that affects everything from our electricity bills to how efficient our entire power grid is. We all learn that basic formula in school, right? Power equals voltage times current. And in the world of DC, like with batteries, it's pretty much that simple. But AC power? Well, that's a different beast entirely. That one simple equation suddenly explodes into three different kinds of power: real, reactive, and apparent. So what's the deal? Why the extra complexity? That's the puzzle we're going to solve today. Here's the game plan. We'll start with the puzzle itself, then we'll meet the key power players and see how they all fit together in something called the power triangle. After that, we'll look at the very real cost of wasted power, see how we can fix it, and finally touch on the ultimate goal for any electrical engineer, getting every last watt of power where it needs to go. All right, so to really get our heads around this puzzle, we have to start at the beginning. There's one core formula for power that's always true, no matter how complicated things get, and this is our launching point for everything else. It all comes down to this: instantaneous power. See, in AC circuits, the voltage and the current are these constantly changing waves. But here's the crucial part. Those two waves aren't always perfectly in sync. They might be a little out of step. And when you multiply them together at every single instant, that misalignment creates a new, much more complicated power wave. And it's inside that complexity that our three different types of power are born. So, from that one complex wave, two main characters emerge. You can kind of think of them as the two sides of the AC power coin, and each one has a very different job to do. On one side, you have real power. This is the workhorse. This is the good stuff, measured in watts, that actually gets a job done. It's what creates the light from a bulb or the motion in a motor. Then you have reactive power. This stuff does no useful work at all. The best analogy is the foam on a beer. It takes up space in the mug, but you can't drink it. It's just energy that sloshes back and forth in the system to build the magnetic fields that things like motors and transformers need to operate. So it's necessary, but it's not the main event. And hey, don't just take my word for it. The source material puts it perfectly. Real power is the useful power. It's the only part of the energy that actually changes from being electrical into something else we can use, like heat, light, or sound. So we've got our useful workhorse power and this sloshing, foamy power. But they don't just exist on their own. They actually combine to create a third and really important concept, which is the total power the grid has to produce and send our way. And that's called apparent power. You can think of it as the total package. It's the combination of both the real power and the reactive power. And from the power company's point of view, this is what really matters. It's the total amount of energy they have to generate and shove through the wires to your house, whether all of it is doing useful work or not. The power triangle is the perfect way to visualize this whole thing. Just picture a simple right-angle triangle. The useful real power is the flat base. The wasted reactive power is the vertical height. And the apparent power, that total power the grid has to supply, is the long side, the hypotenuse. It shows you right away that they don't just add up simply. You need a little geometry to see the full picture. And all this leads us to probably the most important metric for efficiency, the power factor. It's just the ratio of the useful real power to the total apparent power. A perfect power factor of 1 means your system is 100% efficient, all beer, no foam. But a low power factor, like say 0.7, well, that means the power company is sending you a full mug, but 30% of what's inside is just useless foam. Now, this isn't just theory. A low power factor has real-world costs. So let's look at a concrete example from the source material. Imagine an industrial load, like a big motor running in a factory. So here's our setup. We've got a power source, we've got the transmission line to get the power there, and of course the factory motor. Super typical real-world scenario. So how does the power actually shake out? Let's look at the numbers. Okay, so the motor successfully receives 975 watts of real power. This is the good stuff. This is the energy actually spinning the gears and getting the job done. That's fantastic. But, and this is a big but, here's the catch. Because of that poor power factor, the total current flowing in the line is higher than it needs to be. And that extra current creates extra heat. In this case, a full 25 watts of real power is just burned off as heat in the transmission wire. It's just gone, wasted.
That's energy that is literally lost forever for no good reason.
So that leads to the obvious question. Can we do better? Can we stop that waste and get that energy back? You bet we can. The source material poses the perfect engineering challenge here. If we can't change the power company's generator, and we can't change the factory's motor, is there still a way to make the whole system more efficient? The answer is a resounding yes, and it's a pretty clever trick. The solution is called power factor correction. What you do is add a new component, a capacitor, right next to the motor. You can think of it like giving the motor its own little local reservoir for that sloshing reactive power. Now, the capacitor and the motor can just trade that energy back and forth between themselves, so the power grid doesn't have to waste effort sending it all the way down the line. And the results really speak for themselves. Before we added that capacitor, the system efficiency was 97.5%. After adding that one simple part, it jumps up to 98.2%. Now, I know, 0.7% might not sound like a huge leap, but imagine that savings scaled up across thousands of factories, across an entire country's power grid. We're talking about a staggering amount of saved energy and millions of dollars. So, we've seen how to make a system more efficient, but what about the absolute best-case scenario? How do engineers design a circuit to squeeze every single possible drop of power out of a source and deliver it to its destination? Well, there's a recipe for that. It's called the maximum power transfer theorem. And the secret is that to get the absolute most power, your load can't just match the source. It has to be its complex conjugate. Think of it like a perfect dance partner. The resistive parts have to be exactly the same, moving in perfect sync, but the reactive part has to be the exact opposite, so it perfectly cancels out the source's own reactive energy. And this is absolutely crucial. The source material shows us exactly why. In their example, a perfectly matched circuit delivered over 312 watts. But when they only matched the resistance and kind of ignored the reactive part, the power transfer plummeted to just 222 watts. That's a massive drop-off. You absolutely have to respect the entire power triangle to achieve true maximum power. So the next time you plug something in, just remember that hidden dance happening inside the wires. This whole world of real, reactive, and apparent power. It just goes to show that even in our most fundamental technologies, there can be these huge hidden inefficiencies. It really makes you wonder, doesn't it? Where else is wasted energy hiding in plain sight, just waiting for a smarter solution?